Hello, class. Today our group will be reviewing Chapter 11, which is an introduction to bivariate association, which, in further detail, is the measures of association at the nominal level. Now, up until Chapter 11, the statistical methods that we have used only permit us to look at the frequency in which certain numbers or categories occur, look at measures of central tendency, such as means, modes, and medians for one variable, and look at measures of dispersion, such as standard deviation and z-scores for one interval or ratio level variable. Now, what we're going to learn in our bivariate analysis, we'll learn how to look at associations, relationships among two variables, look at measures of the strength of the relationship between two variables, and we'll test the hypotheses about the relationships between two nominal or ordinal level variables. But for this demonstration, we'll only be using nominal variables. Now, for our measures of association at the nominal level, we'll be using a bivariate table, which will display an independent variable, which will be the x variable, a dependent variable, which will be the y variable. Now, in our table, we'll be looking for the conditional distribution of y, which is the results of the dependent variable for a specific category of the independent variable. Now, there are three important characteristics of bivariate associations that we have to find when we find the relationship between two variables. The first that we have to find is, does the association between the two variables actually exist? The second one we have to find is if an association between the two variables does exist, and how strong is that relationship? The final thing we have to find is what is the pattern and or direction of the association between the two variables. So, the first thing we have to find out is, does an association between the two variables actually exist? To find this, we'll use the percentage down, compare across method in our bivariate table. So in our bivariate table, we will detect the percentages down each column of the bivariate table for our variables. Then, we will compare the percentages in the columns across the table. Now, we'll find out if an association exists or doesn't exist by using two different methods. To find out if an association doesn't exist, we'll find out that the conditional distributions of y do not change across the columns in our bivariate table. The second way we'll find out if an association doesn't exist between the two variables is if the obtained chi-square is 0. By finding these, then we'll find out that there is no association between the two variables. If we don't find these, then we'll find out that there is an association, and we can continue. Now, to find out how strong our association is, we'll have to use the maximum difference, which is a quick and easy way of finding it. First, we will determine the column percentages in our bivariate table, like we did when we had to find out if the association existed. Then, we will locate the largest difference of the column percentages in any row of our bivariate table. Finally, we will compare those percentages with the strength of the relationship. Now, to determine how strong our relationship is, we'll use our percentages to determine if it's weak, moderate, or strong. For a weak relationship, the results will be between 0 and 10%. For a moderate relationship, the results will be between 11 and 30%. For a strong relationship, the results will be more than 30%. And that's how we'll find the strength of our association. Now, we will find the pattern or direction of our association for our two variables. To do this, we can either have a negative association or a positive association, and we can use our bivariate table to find out if we have either of those. So, if we have a positive association, then if one variable increases or decreases in value, then the other will do the same. If we have a negative association between the two variables, then if one variable increases or decreases in value, then the other will do the opposite. And that's how we'll find the pattern or direction of our association. Now, there are three formulas that we have to find for our bivariate associations. The three formulas that we have to find are phi, Cramer's V, and lambda. For the phi formula, This formula is particularly used when calculating chi-square-based measures of association for 2x2 tables. So that's tables with 2 rows or 2 columns. Now this formula is fairly easy to calculate. We will simply divide the obtained chi-square by the total number of cases and then take the square root. So we'll have sigma equals square root chi-square divided by n. And here is a good look of our formula. So as you can see, we have phi equals square root chi-square over n, which is the number of cases. The next formula we have to find is Cramer's V. Now, this formula is based on chi-square. It is used for nominal variables that have been organized in a bivariate table that can have any number of rows or columns. So to calculate V, we will divide the obtained chi-square by the minimum value of rows or columns minus 1 multiplied by the number of cases. Then we will take the square root of the whole result. So we will have V equals square root chi-square divided by n multiplied by minimum row minus 1 or column minus 1. So in essence, here is the formula. As we can see, we have our V and equals square root chi squared divided by the number of cases, n, multiplied by minimum row minus 1 or column minus 1. And there's our Cramer's V. Now, to find lambda, we have to first understand what proportional reduction in error is. When we find out what this is, then we can use it for our lambda formula. So, for proportional reduction in error, there are two different predictions about the results of cases that we have to find. The first prediction is that we have to ignore the information of the independent variable and make errors when predicting the results of the dependent variable. For our second prediction, we will take the information of the independent variable into account and predict the results of the dependent variable. With a strong association, then we will have fewer prediction errors. So, for lambda, it's the same as before. It's a measure of association that is used for nominal variables that are organized in a bivariate table. This measure of association is based on proportional reduction of error. First, we'll have to find the number of prediction errors while ignoring the independent variable, as stated before, and then we'll have to find the number of prediction errors while taking the independent variable into account. In essence, our formula will look like this. So we'll have lambda equals E1 minus E2, then we'll divide it by E1. So, going over again, to find lambda and our E1, to find E1, we'll have to subtract the total number of cases by the largest row total. Then, to find E2, we'll have to subtract the column total by the largest cell frequency. After each column is calculated, then we'll add them all together. This is how we'll find lambda in our bivariate table. So now let's look at a scenario. Suppose that Canada wanted to privatize healthcare, but we found out that not every household throughout the country could afford that healthcare. Well, if we were going to use two variables, we would have to find the relationship between the total household income and the state of health throughout the country to determine which households could and could not afford healthcare. What we're going to use is SPSS to create a cross-tabulation between those two variables and find out what percentage of households can and can't afford healthcare. Let's go over to our SPSS demonstration right now. For this SPSS demonstration, we need to find the relationship between the total household income and the state of health. To do this, we must first recode our variables in order for them to be used in our bivariate table. To do this, we will click Transform. Then we will go into Recode into different variables. We will reset our variables, and now we will use new variables. Select our variable, click the arrow button. Now we will change the name of our variable into something different. We'll change it into income 2. We'll click change, and we changed our name. Now we will go into old and new values. Now we will change the range of our value. So we'll go from 1 through 6. And our new value, we'll make it 1. Click the add button from old to new, and there we have it for our first range. For our second range, we'll go through 7 to 9. Our new value will now be 2. Click the add button. Our second range will be from 10 to 11. Our new value will now be 3. We'll click the add button. For our last range, we'll go from 12 to 13. Now, our new value will be 4. Click the add button, and now click continue. And now we have our new variable and a new range for our bivariate table. We will now click OK. Now we will change the range for our other variable. We'll go back into recode into different variables, click reset, select our new variable, click the arrow button. And now we will change the name of this variable to, let's say, health 1. Click change. Now we will go into our old and new variables. Again, we will change the range. We'll make it from 1 to 3, and our new value will be 1. Click the add button. Our next range will be from 4 to 5. New value will be 2. We'll click the add button, and now continue. Once all that is complete, we click OK. Now we will do a cross tabulation of both our variables. We'll go to Analyze, go to Descriptive Statistics, go to Crosstabs. Click Reset, and select our new variables. We'll select Health 1 for rows, Income 2 for columns. We'll now go into Statistics. We will now go into Chi Square for our crosstabs. We'll click Continue. Next we'll go into Cells, click Column, and click Continue. Once all that is done, we click OK, and our cross tabulation is complete.